bit, so I don't know if you can see it. I hope what you see is an animation. A mirror that moves
Seems to
back
be
and forth.
working.
That's brilliant. I think the animation speaks for itself. We have a reference mirror moving back and forth. You have a sample with 3 reflecting layers. And we see the signal that's being detected by the detector as a function of the location of the mirror. And you nicely see the 3 interference fringes corresponding to the 3 layers in the sample. So I'm going to change this again and see if I can grab the screen again on my laptop. Um, okay, so I hope you can see my iPad screen. That is the screen that I draw on now. Is that visible? Yes, good. For some reason, the whole thing with you guys is bigger. I'll change it. Okay. Do it in the chat. All right. Okay, so I showed you the nice animation. So I have a question for you guys. And the question is right here. So in other words, if I look at my interference here, that's the signal my photo detector measures. And I would increase the reference arm power here by a factor of 2. Or I increase the reference arm power with a factor of 2. I would definitely see it here. But will I also see that increase in the reference power in this term here? In other words, what's the origin of this term I just underlined?
Yes, so I think you will see a difference there because the second term, that integral, is formed from the reference and the source. So yeah, if you increase the intensity of the reference, of course, it's gonna influence that underlying term.
Okay, and can you tell me by how much?
So also by 2?
Also by 2. What's your argument for the factor of 2?
It's because you increased the intensity by a factor of 2.
So that interference term, it comes from this one here, right?
Exactly, yes.
And so if the intensity doubles for the reference arm, what does that mean for the E field in the reference arm?
Intensity is formed from the E field multiplied by its conjugate.
Yes.
So
Wouldn't that be a square root of 2, since the intensity is proportional to a square of the electric field?
What do you, Vlad? Do you agree or do you disagree with that argument?
I agree.
Okay, so there we have it, the factor of square root of 2. Right? So the reference arm field doesn't double but increases by a factor square root of 2. So what does that mean for this term here? I mean, the answer is there.
Yeah, so that would be twice the square root of 2, right? So 2 times the square root of 2.
Yeah, okay, I'll give you the 2. But the thing is that it increases with the square root of 2. So increasing the reference, doubling the reference arm power means that the amplitude of this term increases by square root of 2. Right? Agreed. At least I agree. Okay, so now an interesting question. So we know that the reference arm light goes to the reference arm and the sample light goes to the sample. And we get the signal is formed by the interference between the sample and the reference arm. So if I look at my detector and I increase my reference arm power, I double it. Apparently, this interference term becomes bigger. So in other words, I could say that my signal becomes stronger. The amplitude of the interference that I see increases by a factor square root of 2. Isn't that beautiful? I
Uh,
get.
I have another question now. How do you increase the intensity of the reference? I mean, you have one source
Yeah,
and it's from the beam splitter, or how do you increase
yeah, I
the?
know you're absolutely right. I can't increase it just like that, right? But what I want to get at is that the interference fringes that you see, that the amplitude of those fringes depends also on the reference arm power. And what we get at is we can amplify our interference fringes by increasing the reference arm power. And so you could view this increase of the reference arm power as increasing the amplification. Um, it might sound strange, but in fact, interference provides you with lossless amplification of your signal. It's a very, I mean, normally you look at an amplifier, you have your input, you send it into an amplifier, it increases the amplitude, but also at the cost of additional noise. That additional noise is not present here. Okay. Um, let me go into another aspect of OCT, and that is I've dealt with the depth resolution. How well can you distinguish two objects in depth from one another, and that is related to the spectral width of the source. At the same time, we want to have a lateral confinement. We want to know in the X and Y direction, not only in the depth direction, but the X and Y direction, what is the resolution. And for that, we can take a look at the confocal microscopy. And confocal microscopy is a very simple principle. You take a light source and you send the light through a pinhole, so basically some kind of point source here, and with a lens you image your pinhole at a certain location in your tissue. And then the light gets reflected at this particular location in depth, it travels back and would be imaged back into the pinhole of your detector. But you put the beam splitter in between, and so you reflect, let's say, half of the light to a detector, where again you put the pinhole and you detect the light. And if the pinholes match in, let's say, image location, then the light that's reflected from this point, the convergence of the black lines, is nicely imaged to the pinhole and fully detected. But the idea is that light that travels through this tissue, so let's assume this is a tissue border, it gets scattered along the way. So it might as well be scattered at this location here and then travel back. But the lens images this location here over a very large area at the pinhole. The pinhole is not in the image location of this particular location of the tissue. And with the pinhole, you block a lot of light, so you get kind of a discrimination of light that's not coming out of the focal point of the lens. This is what we call confocal microscopy. Okay, confocal microscopy is a very powerful technique. You can create very nicely images, what we call en face images at a particular depth in the tissue, so at a fixed depth of the tissue, and you do that by basically focusing the focal point at different locations in the laterally in the tissue. And these are some examples of the images that you can create. So this is an image of nerve tissue. This is an image of connective tissue, which means collagen. We can look at muscle tissue. This is skeletal muscle. We can look at the blood vessel. So here you have a blood vessel. We can look at adipose tissue. Adipose tissue is fat, and again, skeletal muscle. So the principle of confocal microscopy is based on this pinhole that rejects light. So if we want to have a very accurate resolution in depth, we need a focus that is very sharp. And what do I mean by that? I can image my sample with two different beams. This is one beam. So this is a Gaussian beam. So this is the full width half max width of the beam, or I can image it with a beam like this, where this is the beam. This area is my beam, Gaussian beam being focused, and in this case this is my focused beam. Of course, this second beam here has a very tight focus, very small focus. And so this, for confocal microscopy, this would be the preferred configuration, because you reject the light that does not come out of focus very fast. So the light that you image will probably come out of this area, very small area. However, for this beam here, the one on top, the light probably will come from an area like this. This is not very selective depth imaging. And so for confocal microscopy, you want to use the second configuration. But the thing is that the size of the focus, how narrow you focus here, and the length over which that focus is maintained is correlated. And that is from Gaussian optics, we call that the focus beam waist. The beam waist is this width of the beam, and it's given by, this is the radius W0 is given by the wavelength multiplied by the focal length of the lens, divided by pi divided by W, and W is the beam at the lens. And you can rewrite that in terms of numerical aperture. The ZR is called the Rayleigh range. And the Rayleigh range is the length over which this focus is more or less maintained. So we define the Rayleigh range ZR as the distance over which the W increases to square root times W. So basically the radius of the beam increases by a square root of 2. And so that that definition, the Rayleigh range is given by this expression here. So it's the pi times the diameter of the focus, the radius of the focus squared divided by the wavelength. And so let's take a look at some practical numbers for this. For, let's say, a beam diameter of 30 microns and a beam diameter of 3 microns. So for 30 microns beam diameter, we get a depth of focus of about 1 millimeter. That means that over a length of 1 millimeter, that focus is increase, the diameter increases from 30 micron to 30 micron times square root of 2. If you look at the beam of 3 micron, then that depth of focus is only 10 micron. So in OCT, our fast scan axis is the depth axis. We scan very fast along this direction. That is the motion of the mirror. And as I will show you later, we're not moving mirrors anymore, but we use lasers that sweep with velocities of 100,000 to 1,000,000 times per second. So this is our fast axis. So for good OCT imaging, this situation is not very beneficial because we get a very high spatial resolution, actual resolution, but we have that only over a distance of 10 micron. And in OCT, we're looking over at distances of about a millimeter to 2 millimeter. So the configuration that is much better suited for OCT is this one, 30 micron beam diameter, and you get the depth of focus of about a millimeter. This also shows you that really high resolution imaging with OCT is very difficult. A cell has the diameter of about 10 micron. It's very hard to reach cellular resolution with OCT. But I hope I can convince you that with OCT you can still get very meaningful images of tissue. This is another way of looking at OCT versus confocal microscopy. So you see here the beam waist drawn. And with OCT, your signal comes from a very small block here that is determined by the coherence length of the source. I think this is a material that Dirk already explained to you, that if you look at scattering, then the scattering strength decreases with wavelength. So along this axis is wavelength. This is 500 nanometers. This is 1.3 micron. And this is the scattering strength shown. Oops, the scattering strength in red. I'm pretty sure that looks familiar. Then I also plot the absorption of water, hemoglobin and melanin. This is the yellow is water, and the orange here is blood. And I plot here the resolution versus penetration, where for the resolution I assume the shorter the wavelength, the higher the resolution. Because if we go back to this waist, then we see that if we choose a smaller wavelength, we get a smaller waist, so a higher resolution. So we have resolution versus penetration, but we see then that if we go to the longer wavelength OCT, so let's say 1.3 micron or even 1.7 micron, we can get actually deeper in tissue, but we lose resolution. If you go to the very short wavelength OCT, 500 nanometers or 300 nanometers, we increase resolution, but the scattering increases a lot, which diminishes how deep we can look into tissue. And this is just an example of an OCT image of a fingernail. So what we see here is, well, this is how it was recorded. We have a beam, hits a mirror, it hits a lens that focuses the light, and so the light is basically moving back and forth over the finger right here. And we see here, this is the nail plate. This is the nail. This here is the area where the nail grows. This here is the cuticle, that is that little piece of tissue that is over your nail. And then here you get the rest of your finger with, here you get this part is skin, and here you get deeper into the tissue with, most likely we can see here, blood vessels and other structures. And so this is a nice cross section of a finger, going to about the total size here is 1.2 millimeters and the length is 4 millimeters. Okay, let's go into some nomenclature for OCT. So we can make a single depth scan of the tissue by moving my mirror back and forth once. That is called an A scan, and it looks like this. This is a real signal from a human retina. So you see that it looks very noisy. There's many spikes and it fluctuates a lot. If we create a scan, so we do a transversal scan over the surface of the retina, we have a collection of B scans, a collection of A scans. We call that a B scan, and it allows you to create a cross-sectional image of the tissue of the eye, for instance. So that is shown here. And I don't know if you noticed that, but a single depth profile in this image is actually shown here. So although it looks very noisy, if you turn it into an image, your brain is very good at turning that information, that noisy information, into something meaningful. And then the second thing is that instead of just scanning a single line, like in the B scan, you can scan a full area on the back of the eye. Basically, you have acquired a volume of information now, and out of that volume, you can create an en face projection, which is basically an image as if you were looking at the surface of the retina. Only you can create that en face at multiple depths in the tissue, and that is called a C scan or an en face image. And this is an example of such an en face image in the human eye at optic nerve head. Okay, let me summarize the technique. We get the fringe amplitude of the interference is proportional to the amount of reflected light from a specific depth. The longitudinal or the depth resolution is determined by the coherence gate of the reference arm, and that's determined by the coherence length. And the coherence length in OCT can be as small as 2 micron, but in general it's more on the order of 10 micron. The lateral resolution is determined by focusing optics, similar to confocal microscopy, with the lateral resolution between 5 and 30 micron. And the penetration depth is determined by the scattering coefficient of the tissue, because the signal decays exponentially with depth, and that is due to Lambert-Beer. I'm pretty sure Dirk has already explained. Okay. I'm showing this equation one more time. So this is the equation that we derived. And we already answered the question if the reference arm power doubles. Now in OCT, this is our measured quantity, but in general what we do is we square it. So the signal that we get is the square of the intensity. So the signal, if we talk about signal in OCT, it is in general defined as the square of that measured intensity. Now again, if I look at this signal, I'm going to ask Vlad, if I double my reference arm power, how much will my signal increase now? Signal is intensity squared. How much did the intensity increase if I doubled my reference arm power?
So 2. Because it's the double, it's the squared of the root square of 2, right?
Yeah. And so I type that into my calculator and I get 2, right?
Yeah.
Yeah. Okay. So now in this case, if we define our signal as the intensity that we measure with our detector and then squared, in this case, our signal doubles when we increase the reference arm power. Okay. Normally I do an exercise at this point, but I want to go on a little bit and then after the break have an exercise for you to do. Okay, so the next topic is noise. It sounds boring, but noise actually determines with what precision or with what sensitivity you can measure your signals. And there are basically three noise terms when we measure light with the detector. And the first term is what we call thermal noise. And this is the noise that is generated by the detector itself. And in general, the higher the temperature of the detector, the more noise. So that is why in general, if you want to do a really sensitive measurement, you cool your detector to -10, -20, -80. The second noise term is shot noise, and this is an intrinsic noise term that you cannot avoid, and I will go into detail later. And the third noise term is intensity noise, and this is also noise that is associated with the properties of the source, and in general hard to avoid. I want to skip thermal noise. I mean, it's pretty obvious that any detector that you turn on and you measure the output, it has noise on it. That's the thermal noise. So now I want to go to the duality of light, and I think you're all aware of the fact that light can be described both as a particle and as a wave. And in general, we have the wave picture of light, but there was, of course, the famous experiment describing the photoelectric effect. And the photoelectric effect could only be explained if we assumed that light was actually a particle. So that's why it's a groundbreaking experiment. What happens is we take a material, potassium, and we illuminate it with light. And then it turns out that if we decrease the wavelength, so go from red to blue, at a certain point, electrons are being emitted from the potassium. And so the explanation of this now is that we have a photon that has enough energy to hit an electron out of its orbit into ionization and freeing up that electron. The interesting thing is, if you look at the wave picture for this effect, you would think, well, why don't I just increase the amplitude of my wave? And at some point, I will be able to shake that electron out of its orbit regardless of my wavelength. And that turns out not to be the case. The amplitude of the wave is really independent of the ability to free that electron. And so this led to the particle description of photons. The way it was described now is that the photon is a packet of energy. And if that packet of energy is not energetic enough to free up that electron, it won't happen. The other thing that was nice about this experiment is when you went to the shorter wavelength, so the more energetic photons, and you looked at the energy of the electron that was freed up, you used the shorter wavelength, then more of the energy was converted to a kinetic energy of the electron. So you really needed the particle picture of light to describe the results of this experiment, and that's why it's a groundbreaking experiment. The behavior of light as waves goes far back to the 1800s, you know, Maxwell's equations, Fresnel interference. Anyway, that principal property of light, that it is a particle, still plays a role when we look at the detection of light. Because we have a light source, we can describe it as a stream of waves, but also as a stream of particles that hits our photodetector. And in our photodetector, the stream of light is converted to electrons. And so you can see I have a stream of photons here, And if I assume that every photon leads to one electron being freed in my photodetector, it leads to this stream of electrons. And it's this particle behavior that actually leads to a noise term, because I can look at my stream here of electrons and I can plot then basically the current. And what I see is that that current fluctuates a little bit, just depending on, you know, how many electrons are in this block versus the second block versus the third block. The number of particles just fluctuates a little bit, and that creates a fluctuation in the current, and that's why we call it shot noise. Okay, so this is a fundamental noise term because it's related to the particle character of particle nature of light. You cannot change it. Shot noise is always present. There's no way to get around it. It's a really fundamental noise term. And then if you look at that shot noise current, it is the noise current is given by the square root of 2 times the Q, this is the basic electron charge, times that current times bandwidth, and that's in unit hertz. So do I analyze my noise in a 10 hertz bandwidth or in a 100 kilohertz bandwidth? That makes a difference for the magnitude of that noise term. So let's take another look at this stream of photons and on the noise that it generates. So what I've drawn here is 1, 2, 3, 4, 5, 6, 7 blocks, and the average number of photons in each block is 4. But what we see here is I've shown you the actual number of photons in each block, and as we see the first block, and it's 7, and it's 4, and it's 1, and it's 6, and it's 2, 5, 3. So for each time block, we can calculate. Okay, I have to quickly go to my basic because some symbols in the equations have disappeared. Hold on, bear with me. Here. It's an equal sign, and this is a proportionality sign. Okay. Okay, so if we would calculate, oh, I need one more. We can calculate the noise as the intensity minus the mean and squared. This is called the variance. And if we would calculate the variance for the distribution that I've for the actual measurement that I show you here, what you will see is that this is what it should be. Oh. So the variance squared is equal to the mean itself. And this is a very interesting expression. So the variance is equal to the mean. That is a relatively large noise. In other words, if I take the intensity and I subtract the mean from it, and I take the square of that part, and I do that for every bin that I have, then that term is equal to proportional to the intensity itself. In other words, the noise squared is equal to the is linearly equal to the noise. Sorry, to the intensity. The other important thing is that in general we have to analyze noise in frequency bands. So I can take a detector and I can filter out all high frequencies. Then my noise will be a certain amount. I can also look at the noise in a high frequency band, let's say between 10 kilohertz and 100 kilohertz. So the question then is, what is the fundamental property of shot noise? And it turns out that noise is equal regardless the frequency. We call that a white noise distribution. The noise power in any frequency is equal. And that's, of course, also a very fundamental property. If we would cut off the noise at some higher frequencies, then we could get this pink tail off, this kind of shape. If you have a flat and then it tails off, the name for that in general is pink noise. Okay. Let me quickly. Yeah. Yes, my thingy blinks. Is there? Okay, not important. What is another way of looking at the noise of a thermal light source? I don't know if you had it in your education, but you can look at the Bose-Einstein distribution. That Bose-Einstein distribution gives the probability to measure n photons, given that the mean number of photons is n bar. So I have a stream, I have a light beam. In that light beam, I have on average n bar photons. What is the probability that I measure n photons? I can say my mean is, let's say, 10 or 100 photons. How large is the probability that I, in a given time interval, I measure 90 photons or 12? Well, you can calculate that probability, and that probability is given by this Bose-Einstein distribution. So here we have n bar, here we have n bar, here we have n bar, and here we have the actual number n of the photons that we measure. So we have a full probability distribution. If we have a full probability distribution, you can also calculate the noise. So I can calculate now what is my delta n, what is the variance of that on that stream of photons if I calculate it. And interestingly enough, it turns out that there are two terms. There's one term that is proportional to the mean of the number of photons, and there's a second term that's actually proportional to the mean squared. If you go back to the shot noise, then the shot noise was proportional, the shot noise delta n squared was proportional to the mean of n. Going back to this Bose-Einstein distribution, we see that delta n is proportional to n squared. So this term in that Bose-Einstein distribution explains the shot noise. But apparently there is a second term present. So there is an additional noise going around that stream of photons. And so if you dive into that, it turns out that that noise term actually scales with something that we will call the number of thermal modes. And I won't go into detail, but we see that this term here scales with something that we call a number of thermal modes, but the name we give it is relative intensity noise. So we have the shot noise, that's this term, and we have the second term that is the relative intensity noise. Can I explain relative intensity noise? In a way, it's as follows. I can measure the intensity with a photodetector, and I will see that it fluctuates a little bit. And it turns out that this fluctuation becomes larger if my intensity is larger. So if I measure at a higher intensity, the fluctuations will be larger. So you think, well, that also happened with the shot noise. If my intensity is higher, my shot noise is higher too. But for the intensity, doubling the intensity, the standard deviation here increases by square root of 2. For the intensity noise, that fluctuation increases by a factor of 2. And the reason is that this one scales linearly with n, and this one scales with the square of n. So if you then look at what are the noises that I see on my detector, on this axis is the noise power, and noise power means we're looking at delta n squared, delta n squared. If we have no light falling on our detector, then of course we measure a certain noise level, which is given by the noise of our detector. So this is this line here. This is thermal noise. However, if I increase my intensity, at some point I will see shot noise. So my shot noise increases linearly with delta. And remember, shot noise N was equal to delta N delta N squared. And so when delta N squared increases, the noise also increases. So that's a linear behavior with slope 1. And the thermal noise, sorry, the Bose-Einstein noise, that one increased with the square of the mean N. So there, N squared is equal to delta N squared. And remember, huh, this is the intensity, so this is the N axis. So since the noise here increases with the mean squared, we get a slope of 2 here for the increase of the thermal, of that relative intensity noise. So if we, and this is very general for light detection. Huh?
So since this is quite general, so at some point it's not beneficial anymore to increase the intensity to get a better signal to noise ratio, or?
Let me see. Yes.
Okay, it's quite a difference from what you heard in the bachelor's. So that's interesting.
Well, in the bachelor you deal with this area. In general, where it's assumed that the noise increases with the square root of your intensity.
Yeah.
And then your SNR is given by the intensity divided by the noise. And that increases because your signal, this one goes up linearly, but this one increases with the square root. And your signal to noise keeps increasing. What I show you, at some point, that breaks down. Because then there is this fundamental noise property of light that that starts to dominate. For some intensities, you are reaching this regime, and there's no benefit anymore.
So how does this relate to the reflection, the reference arm intensity?
Yeah, I mean you're spot on. This is where, of course, the problems start to occur, and that is why I put such emphasis on what the reference arm power does, because I can show you a derivation where increasing the reference arm power increases the signal, and you're like, wow, if I want more signal, I just keep increasing my reference arm power. And I need this graph that I show you right now, that at some point, so the way we define signal is that the signal is equal to the intensity squared. So it meant that if I double my reference arm power, my signal doubles. But what it also shows that in this regime, increasing your reference arm power also increases your noise in the same manner, and there's no gain anymore. Okay.
So out of curiosity, in OCT experiments, do you try to go to the outer edges of the second regime?
You try to be right here, smack in the middle.
Okay. But wouldn't it still be beneficial to move a bit more to the right? Or
oh wait, sorry, I have to. The best location is where this line and this line cross, right here. That's the best location. Because this is your fundamental limit, And at this point, they are equal, which means that both contribute the least. But okay, this is way beyond what I expect of the class, so I'm sorry. I think it's time to go to an exercise. So what I will, how can I post an exercise? Normally I hand it out. I'm gonna try and switch to my other screen and then show you the exercise. Let me first bring it up. Okay, so what we do is we take a break until 3:30, and in that meantime, I probably have been able to put that exercise on my slides.